AWS versus Azure versus GCP. Cloud networking compared. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this series, we are going to do a deep, side-by-side comparison of networking constructs across the three major public cloud platforms: Amazon Web Services, Microsoft Azure, and Google Cloud Platform. If you work as a network engineer, cloud architect, or infrastructure specialist, understanding how these platforms map to each other is critical. You might be designing a multi-cloud environment, migrating workloads between clouds, or simply expanding your expertise beyond a single provider. Each cloud platform has evolved its networking model independently, and while there is significant conceptual overlap, the terminology, scope, behavior, and default configurations differ in important and sometimes surprising ways. We will work through the full networking stack from the foundational virtual network construct all the way up to advanced services like private connectivity, service endpoints, DNS, load balancing, and security. The diagram on this slide shows a high-level view of how the three clouds organize their networking. AWS organizes resources under a VPC scoped to a single region. Azure uses a virtual network, also regional, but integrates deeply with its subscription and resource group hierarchy. GCP's VPC is global by design, spanning all regions within a project, which is a fundamentally different model. Each of these foundational differences has cascading implications for how you architect everything else, and we will explore each in detail throughout this series. Subnets. Regional versus zonal versus auto mode. Subnets are the next layer down from the virtual network. They segment the VPC or VNet address space and are where compute resources like virtual machines are actually placed. The scoping of subnets differs significantly across the three clouds. In AWS, subnets are scoped to a single availability zone. This is a very important distinction. If you want high availability across multiple availability zones within a region, you must create a subnet in each availability zone you want to use. For example, to deploy a fault-tolerant application across three availability zones in US East 1, you would create three separate subnets: one in US East 1A, one in US East 1B, and one in US East 1C. Each subnet has its own CIDR block carved from the parent VPC. Subnets in AWS are either public, meaning they have a route to the Internet Gateway, or private, meaning they do not. In Azure, subnets are scoped to a virtual network, which is already regional. Subnets in Azure are not explicitly tied to a specific availability zone. The availability zone association happens at the resource level, not the subnet level. This means an Azure subnet can span all availability zones within a region, and you can deploy zone-redundant resources in the same subnet. Azure also reserves 5 IP addresses in every subnet for internal platform use, which is important when planning your CIDR allocations. In GCP, subnets are regional. They span all zones within a region automatically. A subnet in US Central 1 is available in US Central 1-A, US Central 1-B, and US Central 1-C without any additional configuration. GCP also offers two subnet creation modes. In auto mode, GCP automatically creates one subnet per region when the VPC is created. In custom mode, which is recommended for production environments, you define your own subnets with specific CIDR ranges and regions. Auto mode is convenient but limits your IP address flexibility. Network Address Translation Services. Outbound Internet without public IPs. A critical pattern in cloud networking is providing outbound Internet access to private resources that should not be directly reachable from the Internet, while still allowing them to reach external services for things like software updates, API calls, or telemetry. This is the role of NAT, or Network Address Translation, services. AWS provides the NAT gateway for this purpose. A NAT gateway is deployed into a public subnet and is assigned an elastic IP address. Private subnets then route their internet-bound traffic quad 0/0 to the NAT gateway, which translates the private source IP to its elastic IP before forwarding the packet to the internet. Return traffic is mapped back to the private instance transparently. NAT gateways in AWS are zonal resources for high availability across multiple AZs. You must deploy one NAT gateway per AZ and update each AZ's private subnet route table accordingly. AWS charges per hour that the NAT gateway exists plus per gigabyte of data processed. Azure provides the Azure NAT gateway as its managed outbound NAT solution. Like AWS, an Azure NAT gateway is assigned one or more public IP addresses and is associated with specific subnets. All outbound traffic from those subnets is translated through the NAT gateway's public IPs using SNAT, or Source Network Address Translation. Azure NAT Gateway supports up to 16 public IP addresses per gateway, providing up to 1 million simultaneous SNAT ports for outbound connections, which is significantly more than a single AWS NAT gateway. Azure NAT Gateway is a zonal or zone redundant resource depending on configuration. In GCP, the equivalent service is CloudNAT. CloudNAT is a distributed, software-defined managed service that provides NAT without a central gateway appliance. It is configured per cloud router per region per VPC and applies to selected subnets. GCP Cloud NAT can automatically allocate NAT IP addresses or use manually reserved external IPs. One notable difference from AWS and Azure is that Cloud NAT does not use a dedicated virtual machine or appliance. It is implemented in the GCP network fabric itself, which means it scales automatically and does not become a bottleneck. DNS services. Name resolution in the cloud. Domain name system services are fundamental infrastructure for any cloud deployment, enabling human-readable names to resolve to IP addresses, supporting service discovery, and managing traffic routing based on geographic, latency, or health-based policies. Each cloud has a comprehensive DNS offering. AWS provides Route 53 as its DNS service. Route 53 serves two primary functions. First, it operates as an authoritative public DNS service, where you can register domains, create hosted zones for your domains, and manage DNS records including quad A, CNAME, MX, TXT, and alias records. Second, Route 53 provides private hosted zones for DNS resolution within your VPCs. Private hosted zones are associated with one or more VPCs and resolve names that should not be publicly visible. Route 53 also offers advanced routing policies including simple, weighted, latency-based, geolocation, geoproximity, failover, and multi-value answer routing, making it a powerful traffic management tool beyond basic name resolution. Azure DNS provides public and private zone management. Public Azure DNS zones host domain records accessible from the Internet. Private DNS zones in Azure integrate with VNets through virtual network links, enabling automatic registration of virtual machine hostnames within linked VNets and custom name resolution for private resources. Azure also includes a built-in DNS resolver for VNets. By default, all virtual machines in an Azure VNet can resolve names within that VNet and Azure provided names using the Azure DNS server at 168.63.129.16. Azure Private DNS Resolver is a newer, dedicated service that enables DNS forwarding between on-premises environments and Azure private zones, replacing the need for custom DNS server virtual machines. Google CP's Cloud DNS is a scalable, reliable managed DNS service. Like the others, it supports both public and private zones. Google CP's internal DNS provides automatic name resolution for virtual machine instances using the format instance name.zone.c.project.id.internal. Private DNS policies and DNS peering enable cross-VPC and cross-project name resolution. Google CP also supports DNS forwarding, where queries for specific domains are forwarded to on-premises resolvers, and inbound DNS forwarding, where on-premises resolvers can forward queries to Google CP's managed private zones. Google CP Cloud DNS uses Anycast routing for its name servers, ensuring low latency resolution globally. Private connectivity. Direct Connect, Express Route, and Interconnect. For enterprise workloads requiring dedicated, high bandwidth, low latency, and more reliable connectivity than the public internet, all three cloud providers offer dedicated private connectivity services. These bypass the public internet entirely and connect on-premises data centers directly to the cloud provider's network. AWS Direct Connect provides dedicated physical connectivity between your on-premises environment and AWS. A Direct Connect connection is a dedicated 1 gigabits per second or 10 gigabits per second or 100 gigabits per second Ethernet port at an AWS Direct Connect location, which is a colocation facility where AWS has equipment. From there, you partner with an AWS Direct Connect partner to extend the connectivity to your data center. Direct Connect supports two virtual interface types: private virtual interfaces, or private VIFs, which connect to a specific VPC, and public virtual interfaces, or public VIFs, which access AWS public services without traversing the internet. Transit virtual interfaces connect to a Direct Connect gateway, which can then reach multiple VPCs across multiple regions. Direct Connect does not provide encryption natively. You must layer IPsec over it using a VPN if encryption is required. Azure Express Route provides dedicated private connectivity to Azure. Express Route circuits are purchased with a specific bandwidth from 50 megabits per second up to 100 gigabits per second through an authorized Express Route connectivity provider. Like Direct Connect, Express Route connects at a colocation facility and does not traverse the public internet. Express Route supports two peering types: private peering, which connects to your Azure VNets, and Microsoft peering, which accesses Azure Public Services and Microsoft 365. Express Route Global Reach allows two on-premises locations to communicate with each other through the Azure backbone, effectively using Azure as a transit network. Express Route also supports Express Route Direct, which provides direct 10 gigabits per second or 100 gigabits per second connections to Microsoft's network edge. Google CP Cloud Interconnect offers dedicated interconnect and partner interconnect. Dedicated interconnect provides direct physical connections to Google's network at 10 gigabits per second or 100 gigabits per second at Google colocation facilities. Partner interconnect is available through Google's network service provider partners and supports capacities from 50 megabits per second to 50 gigabits per second, making it accessible for organizations that cannot reach a Google colocation facility directly. Both types use VLAN attachments to connect the interconnect to specific VPCs via Cloud Router. Google CP also provides cross-cloud interconnect for direct dedicated connectivity between Google CP and other cloud providers including AWS and Azure, which is a unique capability not broadly offered by the other two clouds. Network security. Firewalls, security groups, and NSGs. Network security controls govern which traffic is permitted to flow between resources. Each cloud has a layered security model with constructs operating at the instance level, the subnet level, and the VPC level. Understanding these differences is essential for correctly implementing your security posture. AWS uses security groups as the primary instance level firewall. Security groups are stateful, meaning if you allow inbound traffic on a port, the return traffic is automatically allowed without needing an explicit outbound rule. Security groups are attached to network interfaces, not to subnets, and a single ENI can have up to 5 security groups applied simultaneously. Rules in security groups are allowed only there is no concept of an explicit deny. For subnet level control, AWS provides network access control lists, or NACLs. NACLs are stateless, meaning you must define both inbound and outbound rules for bidirectional traffic. NACLs, are evaluated in rule number order and support explicit deny rules, which security groups do not. AWS, Security Hub and Network Firewall provide additional advanced filtering capabilities. Azure's primary instance-level security construct is the Network Security Group, or NSG. NSGs contain inbound and outbound security rules with allow or deny actions, priorities, and can match on source and destination IP, port, and protocol. NSGs can be applied at two levels. At the subnet level, where they affect all resources in the subnet, or at the network interface level, where they affect only the specific resource. Both levels can be applied simultaneously, with the subnet NSG evaluated first for inbound traffic and last for outbound traffic. Azure also provides Azure Firewall, a managed stateful firewall service with FQDN filtering, threat intelligence integration, and DNAT capabilities for centralized policy enforcement. Azure DDoS Protection provides network-level DDoS mitigation. Google Cloud Platform uses a firewall rules model that applies at the VPC level and targets specific instances using network tags or service accounts. Google Cloud Platform's firewall rules are stateful by default and can be ingress or egress rules. Each rule specifies a priority between 0 and 65535, a target defined by a tag or service account, a source or destination, a protocol and port, and an allow or deny action. Lower priority numbers take precedence. Google Cloud Platform also introduced firewall policies, which allow hierarchical policy management across organizations, folders, and projects, enabling centralized governance of firewall rules. Google Cloud Platform Cloud Armor provides DDoS protection and web application firewall capabilities for load balancer-fronted workloads. Google Cloud Platform's use of service accounts as firewall targets is a particularly powerful pattern that ties firewall rules to identity rather than just network topology. VPC and VNet peering. When you need resources in separate virtual networks to communicate with each other, each cloud platform provides a peering mechanism that connects two networks at the networking layer without routing traffic through the public internet or through a gateway device. Peering is one of the most commonly used inter-network connectivity patterns in cloud environments. In AWS, the mechanism is called VPC peering. A VPC peering connection creates a direct network route between two VPCs, allowing instances in either VPC to communicate using private IP addresses. VPC peering can be established between two VPCs in the same account, across different accounts, and even across different regions, the latter being called inter-region VPC peering. However, AWS VPC peering is non-transitive. This means that if VPC-A is peered with VPC-B, and VPC-B is peered with VPC-C, traffic from VPC-A cannot reach VPC-C through VPC-B. Each peering relationship must be explicitly created. Additionally, peered VPCs cannot have overlapping CIDR blocks, a constraint that applies across all three cloud platforms. Azure uses the term virtual network peering for connections within the same region, and global VNet peering for connections across different Azure regions. Like AWS, Azure peering is non-transitive by default. Azure does offer a mechanism called gateway transit, which allows a peered VNet to use the VPN gateway or ExpressRoute gateway in the hub VNet, enabling traffic to flow from spoke VNets through the hub and onto on-premises networks without each spoke needing its own gateway. This is a significant capability for hub and spoke designs. Google GCP VPC peering connects two VPC networks so that resources in each can communicate using internal IP addresses. Because Google GCP VPCs are global, Google GCP peering automatically enables connectivity across all regions in both VPCs. Like AWS and Azure, Google GCP peering is non-transitive, and peered VPCs cannot have overlapping subnet CIDR ranges. One Google GCP specific limitation is that peered networks do not share firewall rules, routes, or VPN connectivity. Each network maintains its own independent policy. Google CP has a maximum of 25 peering connections per VPC network. Private link, service endpoints, and private service connect. A critical networking pattern in all three clouds is the ability to access platform-managed services such as object storage, databases, and software as a service APIs from within your private virtual network without routing that traffic over the public internet. Each cloud implements this with slightly different architectures and scoping rules. AWS offers two mechanisms for this. The first is VPC endpoints, which come in two types. Interface endpoints create an elastic network interface, or ENI, with a private IP address in your subnet that serves as the entry point for traffic destined for a supported AWS service. The traffic flows from your VPC to the service privately through AWS's network. Gateway endpoints are the second type and work differently. They are route table entries that direct traffic for specific services, currently only Amazon S3 and DynamoDB, directly through the AWS network without using an ENI. AWS Private Link is the underlying technology for interface endpoints and also allows AWS customers to expose their own services to other VPCs through a service provider model, enabling private software as a service connectivity across account boundaries. Azure provides two parallel mechanisms. Service endpoints extend your VNet identity to Azure Service Resources, allowing you to secure Azure Storage, SQL Database, Cosmos DB, and other services to your VNet by adding a service endpoint to a subnet. However, traffic still leaves your VNet and traverses the Azure backbone to reach the service. It is not a fully private path. Azure Private Endpoint is the more complete private access solution. A private endpoint creates a private IP address in your subnet backed by a private link resource, and all traffic to the target service flows through that private IP entirely within the Azure network. Private endpoints support third-party services and custom services in addition to first-party Azure services. Google CP provides Private Service Connect, or PSC, as its unified solution for private access to managed services. PSC creates an endpoint a forwarding rule with a private IP in your VPC that connects to a PSC service attachment published by a service producer. Google CP uses PSC for accessing Google APIs such as cloud storage and BigQuery privately without using external IPs. PSC also supports inter-VPC service consumption through a producer-consumer model where service producers publish PSC service attachments and consumers create PSC endpoints to access those services. Google CP also provides private Google access at the subnet level, allowing virtual machines without external IPs to reach Google APIs using the googleapis.com address range privately. CDN services. CloudFront, Azure CDN and Front Door, Cloud CDN. Content delivery networks accelerate the delivery of web content, APIs, and media by caching content at edge locations geographically distributed around the world, reducing the distance between the content and the end user and offloading traffic from origin servers. Each cloud provider offers CDN services tightly integrated with their networking and security ecosystems. AWS CloudFront is AWS's CDN service with a global network of edge locations. CloudFront distributes content from origins, which can be S3 buckets, EC2 instances, application load balancers, or any custom HTTP server. CloudFront caches responses at edge locations based on cache behaviors, which are path pattern rules that define caching TTL, allowed HTTP methods, query string forwarding, and cookie handling. CloudFront integrates tightly with AWS Shield for DDoS protection and AWS Web Application Firewall for Layer 7 filtering at the edge. CloudFront functions and Lambda at edge allow you to run code at edge locations to modify requests and responses. Functions for lightweight transformations and Lambda at edge for heavier processing. CloudFront supports HTTPS with custom secure sockets layer certificates via AWS Certificate Manager and provides real-time metrics and access logs. Azure offers CDN capabilities through two primary services. The original Azure CDN service, available through multiple CDN provider profiles including Microsoft, Verizon, and Akamai, provides standard caching and delivery acceleration. Azure Front Door, on the other hand, is Azure's modern, globally distributed entry point service that combines CDN caching, global HTTP load balancing, secure sockets layer offloading, web application firewall, and URL-based routing into a single service. Front Door uses Microsoft's global WAN backbone rather than the public internet for routing traffic from edge to origin, which provides performance advantages. Front Door's Anycast architecture means users connect to the nearest front door point of presence, or POP, and traffic is then routed optimally to the origin. Front Door Standard and Premium SKUs unify CDN and security capabilities with deeper web application firewall integration in the premium tier. Google Cloud Platform provides Cloud CDN, which integrates directly with Google's external HTTP/HTTPS load balancer. Cloud CDN caches content at Google's globally distributed edge network, which leverages the same infrastructure used by Google's own products. Origins for Cloud CDN can be Google Cloud Platform backend buckets backed by cloud storage, backend services backed by instance groups or NEGs, or external origins outside Google Cloud Platform. Cloud CDN supports cache keys, cache modes including cache all static and use origin headers, signed URLs and cookies for private content protection, and negative caching for controlling error response caching. A key advantage of Google Cloud Platform Cloud CDN is its tight integration with the global load balancer, meaning the same Anycast IP serves both load balancing and CDN edge functions without additional configuration. Shared networking. Shared VPC, hub and spoke VNets, and GCP shared VPC. Large organizations with multiple teams, projects, or business units need a way to centralize network management while still giving individual teams the autonomy to deploy their own resources. Each cloud provides a mechanism for sharing networking resources across organizational boundaries. AWS RAM, or Resource Access Manager, allows you to share VPC subnets across multiple AWS accounts within the same AWS organization. This is the foundation of the AWS shared VPC model, though AWS calls it VPC sharing. In this model, a central network owner account creates and manages the VPC, subnets, route tables, and gateways. Participant accounts are then granted access to specific subnets within that VPC and can deploy their own EC2 instances, RDS databases, and other resources into those shared subnets. The participant accounts own and manage their own resources, but the network infrastructure is owned and controlled centrally. This eliminates the need for inter-account VPC peering for teams that need to share common network infrastructure while maintaining billing and resource separation. Azure's approach to shared networking is built around the hub and spoke topology rather than subnet sharing. A central hub VNet hosts shared services like Azure Firewall, VPN Gateway, Express Route Gateway, and DNS servers. Spoke VNets contain workload resources and peer to the hub using VNet peering with gateway transit enabled, allowing spokes to use the hub's gateways for on-premises connectivity without each spoke needing its own. Azure's subscription model supports separate subscriptions for the hub and each spoke, with peering across subscriptions. Azure Landing Zone architecture formalizes this into a reference architecture called the connectivity subscription, which owns the hub VNet, and workload subscriptions, which own spoke VNets. Azure Firewall Manager provides centralized policy management across all hubs in a virtual WAN topology. Google CP provides a feature called Shared VPC that allows a host project to share its VPC network subnets with service projects. The host project owns the VPC, subnets, routes, and firewall rules. Service projects are attached to the host project and can create virtual machine instances in the shared subnets, with the virtual machines receiving internal IPs from the host project's subnet ranges. This is the closest analog to AWS VPC sharing. Service project administrators can deploy resources into shared subnets without having visibility into or control over the underlying network configuration. Google CP also supports IAM-based subnet-level sharing, where specific service project users are granted the compute network user role on individual subnets, enabling fine-grained control over which teams can use which network segments. Network performance, bandwidth, placement, and acceleration. Raw network performance throughput, latency, and jitter can be a critical factor for high-performance computing workloads, real-time applications, and large-scale data transfer. Each cloud provides mechanisms to maximize network performance at the instance and cluster level. AWS provides enhanced networking for EC2 instances through two technologies. The first is the Elastic Network Adapter, or ENA, which supports network speeds up to 100 gigabits per second on supported instance types. The second is the Elastic Fabric Adapter, or EFA, which is a specialized network interface for high-performance computing workloads that require low latency and high bandwidth between instances, such as tightly coupled simulations and machine learning training jobs. EFA supports OS bypass, allowing applications to communicate directly with the network hardware without going through the operating system kernel, dramatically reducing latency. AWS placement groups provide three strategies for controlling instance placement. Cluster placement groups pack instances into the same underlying hardware for maximum network throughput and minimum latency. Spread placement groups distribute instances across distinct hardware to minimize correlated failures. Partition placement groups divide instances across separate logical partitions backed by independent hardware for large distributed workloads. Azure provides accelerated networking for virtual machines, which enables single ROT I/O virtualization, or SR-IOV, to bypass the hypervisor and connect the virtual machine's network interface directly to the physical network interface card. This eliminates virtual switching overhead, reduces central processing unit utilization, and provides significantly lower latency and higher throughput. Accelerated networking is supported on most modern Azure virtual machine sizes. For ultra-low latency clustering, Azure provides proximity placement groups, which request that a set of virtual machines be placed physically close together in the Azure data center, minimizing network latency between them. Azure also provides InfiniBand-connected virtual machine sizes in the H&N series for high-performance computing workloads, enabling RDMA communication at extremely low latency for tightly coupled parallel applications. Google CP provides high-performance networking through several mechanisms. Google CP's virtual machine instances connect to the virtual network through the Andromeda virtualization stack, Google CP's in-house software-defined networking system. Google also offers Tier 1 networking performance for virtual machines, which provides increased egress bandwidth and lower latency by allocating more network capacity at the virtual machine level. For HPC workloads, Google CP provides compact placement policies that collocate virtual machine instances within the same cluster for minimum network latency. Google CP also supports RDMA over Converged Ethernet, or ROCE, for HPC virtual machine families including A3 and H3 instances. The Google Virtual NIC, or GVNIC, is Google CP's high-performance virtual network interface that supports larger packet sizes and higher throughput compared to the default VirtIO interface. Network topology design patterns across the three clouds. Architectural patterns for cloud network topology have evolved to address common requirements including security, isolation, shared services, and scalability. While the building blocks differ across clouds, the underlying design patterns are largely analogous. Understanding these patterns and their cloud-specific implementations is essential for designing robust, scalable network architectures. The hub-and-spoke topology is the most widely adopted enterprise network architecture across all three clouds. In this pattern, a central hub VPC or VNet hosts shared infrastructure firewalls, gateways, DNS servers, and monitoring tools, while spoke VPCs or VNets contain workload resources organized by application, environment, or business unit. In AWS, hub and spoke is implemented using Transit Gateway as the hub, with VPC attachments as spokes. In Azure, the pattern uses a hub VNet with paired spoke VNets or, at larger scale, Azure Virtual WAN hubs. In GCP, the pattern uses Network Connectivity Center or VPC peering from workload VPCs to a shared services VPC. The hub and spoke pattern centralizes security inspection and simplifies routing management compared to full mesh peering. The flat network pattern, where all workloads reside within a single large VPC or VNet, is simple to manage for smaller deployments but creates security and blast radius challenges at scale. Each cloud places limits on the size of a single VPC. AWS limits VPCs to a default of 5 per region. Azure limits VNets to 50 per subscription per region by default. And GCP allows up to 25 VPC networks per project, all adjustable through quota requests. The flat model is most practical in GCP because of the global VPC design, where subnets across all regions can coexist in one network. The multi-account or multi-subscription segmentation pattern extends network isolation to the organizational account level. In AWS, this is implemented through AWS organizations with separate VPCs per account, connected via Transit Gateway. In Azure, this maps to the landing zone model with separate subscriptions per workload tier. In GCP, separate projects own separate VPCs or attach as service projects to a shared host VPC. This pattern provides the strongest security isolation because blast radius from a compromised account is limited to that account's network, and IAM policies can be enforced independently per account. The trade-off is operational complexity in managing cross-account routing, security group references, and DNS resolution. Route tables and user-defined routing. Route tables are the control plane that governs how packets are forwarded within and between subnets, VPCs, VNets, and external networks. Each cloud automatically populates route tables with system-generated routes for local subnets, and provides mechanisms for operators to add custom routes that override or supplement those defaults. Understanding routing behavior is foundational to controlling traffic flow, inserting security appliances, and enforcing traffic inspection policies. In AWS, route tables are associated with subnets. Every subnet must have exactly one route table, though multiple subnets can share a route table. AWS automatically adds a local route for the VPC CIDR that cannot be deleted, ensuring all subnets within a VPC can communicate by default. Beyond the local route, you add entries to direct traffic to Internet gateways, NAT gateways, transit gateways, virtual private gateways, VPC peering connections, or network interfaces. AWS also supports gateway route tables, which can be associated with an Internet gateway or virtual private gateway to inspect or redirect traffic entering or leaving the VPC. This is used for inline security appliance insertion. AWS supports the longest prefix match rule, where more specific routes take precedence over less specific ones. In Azure, route tables are called user-defined route tables, or UDRs, and are associated with subnets. Azure automatically creates system routes for local VNet traffic, VNet peering routes, and routes for on-premises connectivity through VPN or ExpressRoute gateways. UDR entries can point to next hop types including virtual network gateway, virtual network, Internet, virtual appliance, which is a specific private IP address of an NBA or none, which drops traffic. The virtual appliance next hop type is extensively used to force traffic through Azure Firewall or third-party NBAs for inspection. Azure also has a concept of border gateway protocol route propagation that can be disabled on a UDR table to prevent gateway-learned routes from overriding your custom routes. In Google CP, routing is handled at the VPC level, not the subnet level. RAWs in Google CP apply to all instances in the VPC by default. or can be scoped to specific instances using network tags. Google CP has two categories of RAWs. System-generated RAWs include the default route for Internet traffic and subnet RAWs automatically created for each subnet. Custom static RAWs allow you to define specific destination CIDRs with a next hop that can be a default Internet gateway, a specific instance, a forwarding rule for an internal load balancer, a VPN tunnel, or a cloud router for dynamic routing. Policy-based routing, a newer Google CP feature, allows you to route traffic based not just on destination IP but also on source IP, protocol, and port, enabling more granular traffic steering than traditional longest prefix match routing. Kubernetes and container networking. Container orchestration platforms like Kubernetes have become the dominant workload deployment model for modern applications. Each cloud provider's managed Kubernetes service has a distinct networking architecture that determines how pods communicate within a cluster, how services are exposed, and how the cluster integrates with the underlying cloud VPC or VNet. Understanding these networking models is critical for designing secure, scalable container platforms. AWS Elastic Kubernetes Service, or EKS, uses the VPC Container Networking Interface plugin, known as the AWS VPC CNI. With this plugin, every pod in the cluster receives an IP address directly from the VPC subnet. Pods are first-class citizens in the VPC routing table and can be reached directly using VPC routes, security groups, and VPC flow logs. This is a flat, non-overlay networking model. Worker nodes have multiple elastic network interfaces, and each ENI can hold multiple secondary IP addresses, one per pod. The number of pods per node is therefore limited by the instance type's ENI and IP limits. AWS also supports security groups for pods, allowing you to apply EC2-style security group rules directly to individual pods rather than only at the node level. EKS supports both managed node groups and Fargate for serverless pod execution. Azure Kubernetes Service, or AKS, supports multiple CNI plugins with different networking models. The Azure CNI plugin, similar to EKS, assigns each pod an IP address from the VNet subnet, making pods routable within the VNet without NAT. This requires pre-allocating a large subnet because every pod consumes a VNet IP. The KubeNet plugin, on the other hand, assigns pods IPs from a separate pod CIDR range that is not routable within the VNet node to pod communication uses NAT. Azure CNI Overlay is a newer mode that assigns pods from a private overlay address space while nodes get VNet IPs, reducing IP consumption. AKS integrates with Azure Load Balancer for Kubernetes Load Balancer services and with Application Gateway for Kubernetes Ingress Controllers through the Application Gateway Ingress Controller, or AGIC. Google Kubernetes Engine, or GKE, uses VPC native networking by default, where pods receive IP addresses from a secondary CIDR range configured on the Google CP subnet. Each node is allocated a /24 block from the pod CIDR, supporting up to 110 pods per node. Because pod IPs are secondary ranges on Google CP subnets, they are raw table within the VPC and visible in VPC flow logs. GKE Autopilot enforces VPC native networking and manages node infrastructure entirely. For service-to-service communication, GKE integrates with Google Cloud Service Mesh, which is based on Istio and Anthos Service Mesh, providing MTLS between services, traffic management, and observability. GKE also provides a built-in integration with cloud load balancing for external and internal Kubernetes services, and with GCP managed certificates through Certificate Manager. Service Mesh and East-West microservice networking. As applications decompose into microservices, the communication between those services, often called east-west traffic, becomes a critical plane requiring observability, security, and reliability controls. A service mesh is a dedicated infrastructure layer that handles service-to-service communication, providing mutual TLS authentication, traffic management, circuit breaking, retry logic, and distributed tracing without requiring changes to application code. AWS provides several options for secure service edge. AWS App Mesh is a managed service mesh based on Envoy proxy, where an Envoy sidecar is injected into each service container or task and intercepts all inbound and outbound traffic. App Mesh provides traffic routing controls including weighted routing for canary deployments, circuit breaker configuration, retry policies, and health checks. Observability is provided through integration with CloudWatch, X-Ray for distributed tracing, and CloudWatch Container Insights. AWS has also introduced AWS Lattice, a more recent application layer networking service that simplifies service-to-service connectivity across VPCs and accounts without requiring a sidecar proxy model, using the VPC Lattice data plane instead. Azure provides Azure Service Mesh, formerly Open Service Mesh, now based on the Istio specification, as an AKS add-on. The Istio-based add-on for AKS provides automatic sidecar injection, mutual TLS between services for zero-trust networking within the cluster, fine-grained traffic policies including header-based routing, fault injection for chaos testing, and integration with Azure Monitor for telemetry. For non-containerized workloads, Azure Kubernetes Fleet Manager provides multi-cluster service mesh capabilities. Azure also supports Dapr, the Distributed Application Runtime, as an AKS extension, which provides service invocation, state management, pub-sub messaging, and other building blocks for microservice communication without a traditional service mesh architecture. Google CP provides Cloud Service Mesh, its managed Istio-based service mesh, as a managed offering for GKE clusters. Google CP's Service Mesh provides automatic MTLS between all enrolled services, rich traffic management policies including traffic splitting, fault injection, and timeout configuration, and deep integration with cloud monitoring, cloud logging, and CloudTrace for observability. Google CP uniquely offers a managed control plane option where Google CP manages the Istio control plane components, relieving operators of the burden of running and upgrading Istio. For multi-cluster service mesh across GKE clusters in different regions or projects, Google CP Anthos extends the mesh across clusters using a common control plane, enabling unified service discovery and policy enforcement across a fleet of clusters. SD-WAN integrations with cloud networking. Software-defined wide area networking, or SD-WAN, is a technology that abstracts WAN connectivity from the underlying transport and applies software-defined policies to route traffic intelligently across multiple Internet, MPLS, or LTE connections. As enterprises migrate workloads to the cloud, the integration between SD-WAN platforms and cloud networking becomes critical for achieving consistent policy, visibility, and performance from branch offices to cloud workloads. AWS integrates with SD-WAN through the AWS Transit Gateway Connect feature and through the Managed SD-WAN program. Transit Gateway Connect supports the generic routing encapsulation, or GRE, tunnel attachment type and dynamic BGP peering between the Transit Gateway and SD-WAN virtual appliances running in the VPC. SD-WAN vendors including Cisco, VMware, Palo Alto, and others publish SD-WAN virtual appliance AMIs in the AWS marketplace and provide integration guides for connecting their SD-WAN fabric to AWS. The AWS Cloud WAN service extends this further by providing a global managed network built on AWS backbone infrastructure, with segment-based routing and policy-based traffic management that SD-WAN vendors can integrate with through the Cloud WAN API and Network Manager. Azure integrates SD-WAN through Azure Virtual WAN, which provides a native branch connectivity framework that many SD-WAN vendors have certified integrations with. The Virtual WAN partner ecosystem includes vendors such as Cisco, VMware SD-WAN, Barracuda, Citrix, and others. These vendors deploy their SD-WAN branch CPE devices on premises and their cloud-based control plane as Azure Marketplace appliances, with the data plane terminating at the virtual WAN hub via automated IPsec or BGP over MPLS. Azure Virtual WAN's automated branch connectivity simplifies configuration by allowing SD-WAN devices to self-register with the hub using pre-shared keys distributed through the virtual WAN management plane. The result is a zero-touch provisioning model for new branch sites. Google CP integrates SD-WAN through the Network Connectivity Center router appliance spoke type. Router appliance allows third-party SD-WAN and routing virtual appliances deployed as Google CP virtual machine instances to participate in the NCC hub and spoke topology. The router appliance virtual machine establishes a BGP session with Cloud Router in the same VPC, and NCC then advertises routes between the router appliance and other NCC spokes including Cloud Interconnect and HAVPN. SD-WAN vendors including Cisco Catalyst SD-WAN, VMware SD-WAN, and Palo Alto Prisma SD-WAN have certified their virtual appliances as Google CP router appliances, enabling end-to-end SD-WAN fabric that extends seamlessly into Google CP. This integration allows the SD-WAN platform to manage traffic steering policies for Google CP-bound traffic using the same policy engine used for all WAN traffic. Compliance and network segmentation for regulated workloads. Regulated industries including financial services, healthcare, government, and critical infrastructure require network architectures that satisfy compliance frameworks such as PCI DSS, HEPA, FedRAMP, ISO 27001, and SOC 2. These frameworks impose requirements for network segmentation, access control, audit logging, encryption in transit, and the ability to demonstrate that sensitive workloads are isolated from untrusted networks. Each cloud provides specific features and certifications to support compliant architectures. AWS provides AWS GovCloud regions, which are isolated from standard AWS regions and support U.S. government compliance requirements including FedRAMP, HIE, Department of Defense SRG, IL4 and IL5, and ITAR, for payment card industry data security standard environments. AWS recommends isolating cardholder data environments in dedicated VPCs with no shared subnets with non-payment card industry workloads, strict security group rules limiting access to only required services, VPC, flow logs enabled for all subnets in scope, AWS config rules for continuous compliance monitoring, and AWS CloudTrail for API audit logging. AWS Macy provides sensitive data discovery in S3 to help identify data in scope for compliance. AWS Network Firewall can enforce domain-based egress filtering to limit cardholder data environment outbound connectivity to only approved destinations, a common payment card industry requirement. Azure provides Azure Government Cloud regions for U.S. government workloads with FedRAMP High, Department of Defense IL2 through IL5, and ITAR authorizations. Azure Policy provides a compliance framework with built-in policy initiatives for PCI DSS, HIPPA, HITrust, NIST SP 800-53, and other standards that can be assigned at management group scope to enforce network configurations across all subscriptions. Azure Blueprints enables packaging of policy assignments, role assignments, and resource templates into repeatable compliance configurations. For network segmentation, Azure dedicated hosts and isolated virtual machine sizes ensure that sensitive workloads run on hardware not shared with other customers. Microsoft Defender for Cloud provides a continuous security posture management score with network-specific recommendations for NSG hardening, just-in-time virtual machine access, and adaptive network hardening that tightens security group rules based on observed traffic patterns. Google Cloud Platform provides assured workloads as its compliance boundary framework, allowing organizations to create compliance-controlled folder environments that enforce data residency, access controls, and personnel restrictions. Google Cloud Platform's VPC service controls provide a powerful compliance mechanism by defining security perimeters around Google Cloud Platform services. Within a perimeter, Google Cloud resources can communicate freely, but access from outside the perimeter, including from the Internet or from other Google Cloud Platform projects, is blocked at the API level regardless of IAM permissions. This provides defense in depth against data exfiltration and unauthorized access, and is particularly valuable for protecting BigQuery datasets, cloud storage buckets, and other data services containing sensitive information. Access Context Manager works with VPC service controls to implement attribute-based access policies that consider the client device, IP address, and user identity when evaluating access to protected resources. Multicast, broadcast, and anycast in cloud networks. Standard cloud virtual networking is built on unicast communication packets from one source to one destination. However, traditional enterprise applications and network services sometimes require multicast, which delivers packets from one source to multiple receivers simultaneously, or rely on broadcast for neighbor discovery and address resolution. Additionally, anycast is used extensively in cloud platforms themselves for routing to the nearest endpoint. Understanding what each cloud supports and what alternatives exist is important when migrating legacy applications. Multicast is not natively supported in any of the three clouds' standard VPC or VNet environments. The underlying software-defined networking fabric in AWS, Azure, and GCP does not replicate multicast packets to multiple destinations within the virtual network. AWS explicitly states that multicast is not supported within VPCs. However, AWS Transit Gateway does support IP multicast as a feature when enabled on the TGW, allowing multicast sources and receivers connected via TGW attachments to participate in multicast groups. This is a notable exception and makes TGW a potential platform for legacy multicast-dependent applications that cannot be refactored. Azure and GCP do not offer managed multicast through their transit services, though third-party multicast overlay solutions using encapsulation can be deployed as virtual machine-based appliances. Broadcast is not supported in any cloud VPC or VNet. ARP broadcasts, for example, are handled by the Cloud Network Fabric's proxy ARP mechanism rather than being flooded. This is by design and is a fundamental property of the cloud networking model. Applications that depend on broadcast for service discovery must be refactored to use unicast-based alternatives such as DNS service discovery, service registries like Console or etc., or cloud-native service discovery mechanisms. AWS Cloud Map, Azure Service Discovery, and GCP Service Directory provide unicast-based service discovery that replaces broadcast-dependent patterns. Anycast is used extensively in cloud platforms for their global load balancing, CDN, and DNS services. Google CP's external HTTP/HTTPS load balancer uses Anycast to direct users to the nearest edge point of presence using a single global IP address. AWS CloudFront and Route 53 use Anycast for their edge networks. Azure Front Door uses Anycast for its global point of presences. Within customer VPCs, Anycast is not supported for custom addresses. However, a pattern for deploying Anycast-like behavior within a cloud environment uses multiple virtual machine instances in different regions advertising the same IP via BGP through Cloud Router or Virtual Private Gateway, creating regional prefix announcements that effectively implement Anycast routing for hybrid on-premises to cloud traffic paths. This technique is used by customers who need to maintain consistent IP addresses across regions for legacy application compatibility. BGP and dynamic routing in cloud networks. Border Gateway Protocol, or BGP, is the exterior gateway protocol used on the Internet to exchange routing information between autonomous systems. In cloud networking, BGP is the standard protocol used to dynamically exchange route prefixes between cloud networks and on-premises routers over VPN, Direct Connect, Express Route, and cloud interconnect connections. Dynamic BGP routing eliminates the need to manually configure static routes for every on-premises subnet, and automatically propagates route changes when on-premises networks expand or topology changes. In AWS, BGP is managed through virtual private gateways, transit gateways, and the Direct Connect service. When you create a site-to-site VPN connection with BGP, each of the two IPsec tunnels establishes a separate BGP session between your customer gateway router and the AWS BGW. AWS assigns an Autonomous System Number, or ASN, to the BGW. You can use a private ASN in the range 64512 to 65534, or the AWS default of 64512. Your on-premises router uses its own ASN. AWS advertises the VPC CIDR block over BGP to your router, and your router advertises on-premises prefixes to AWS. Learned routes from Direct Connect and VPN are automatically installed into the VPC route table when route propagation is enabled on that route table. AWS recommends using specific prefix advertisements rather than summarized routes for more precise traffic control. In Azure, BGP is used with VPN Gateway and ExpressRoute. For VPN Gateway, BGP peering is established between your on-premises router and the Azure VPN Gateway over the IPsec tunnel. Azure requires that your BGP peer IP be within the BGP peering subnet A/30 block and that you not use ASN 65515, which Azure reserves. Azure VPN Gateway supports multi-site BGP with route discrimination using AS path prepending and BGP communities. For ExpressRoute, Azure uses BGP peering on private peering circuits between your Edge router and the Microsoft Edge routers in the ExpressRoute provider's facility. Azure also supports bidirectional forwarding detection, or BFD, over BGP on both VPN Gateway and ExpressRoute to enable faster failure detection. In Google CP, BGP is managed through Cloud Router, which is a fully managed distributed BGP routing daemon that runs in the Google CP network fabric. Cloud Router is created in a specific VPC and region and establishes BGP sessions with on-premises routers over HAVPN or Cloud Interconnect VLAN attachments. Cloud Router automatically advertises subnet routes for the VPC to the on-premises peer and installs learned routes into the VPC's routing table. Cloud Router supports BGP communities for route filtering and MED, which stands for Multi-Exit Discriminator, attributes for influencing path selection. Google CP also supports custom route advertisements on Cloud Router, allowing you to advertise specific IP ranges, including summary routes or non-VPC ranges such as Cloud SQL or memory store IP addresses, to your on-premises routers. Elastic and static public IP addresses. Public IP addresses are required for resources that need to be directly reachable from the Internet, for resources that act as the source of outbound Internet traffic through NAT, and for services like VPN gateways and load balancers. Each cloud has a distinct model for allocating, assigning, and reserving public IP addresses, with important differences in persistence, billing, and mobility. AWS uses two categories of public IP addresses. The first is dynamic public IP addresses, which are automatically assigned to EC2 instances in public subnets when launched with the auto-assign public IP setting enabled. These addresses are ephemeral. They change when the instance is stopped and restarted, and are released when the instance is terminated. The second category is elastic IP addresses, or EIPs, which are static public IP version 4 addresses allocated to your AWS account and under your control. An EIP remains in your account until you explicitly release it. You can assign an EIP to an EC2 instance, a NAT gateway, or a network interface, and you can move it between resources within the same region. AWS charges for EIPs that are allocated but not associated with a running instance, incentivizing you to release unused addresses. AWS also supports Bring Your Own IP, or BYOIP, allowing you to advertise your own public IP version 4 or IP version 6 CIDR blocks into AWS. Azure manages public IP addresses through a dedicated public IP address resource. Azure public IPs come in two SKUs, Basic and Standard. The Basic SKU is being retired and supported only legacy deployments. The Standard SKU is the current recommended type and is required for use with Standard Load Balancer, Application Gateway version 2, Azure Firewall, and VPN Gateway. Standard public IPs are zone redundant by default, meaning they survive the failure of a single availability zone. Public IP addresses in Azure are either dynamic, assigned at runtime and potentially changing on stop and start, or static, reserved and fixed for the lifetime of the resource. Static standard public IPs are billed by the hour regardless of association, while dynamic basic IPs are free when not associated. Azure also supports public IP prefixes, which allow you to reserve a contiguous block of public IP addresses from Azure's pool, useful for listing a range of your IPs in partner firewalls. In GCP, public IP addresses are called external IP addresses and exist in two modes. Ephemeral external IPs are assigned to virtual machine instances at startup from GCP's pool of addresses for that region and are released when the instance is stopped or the interface is released. They can change each time the instance starts. Reserved, or static, external IPs are reserved in a region or globally. Global IPs are used only with global load balancers and are assigned to specific resources. Static external IPs persist until explicitly released and are charged at a low hourly rate when not in use. GCP also provides premium Tier 1P addresses, which use Google's global backbone for routing, and standard Tier 1P addresses, which use the public internet for routing outside the originating region. A billing and performance distinction unique to GCP among the three clouds. Traffic mirroring and packet capture. Security operations, network forensics, intrusion detection, and deep application troubleshooting all require the ability to capture actual packet data flowing through the LAN, not just metadata like flow logs provide. Each cloud offers packet capture or traffic mirroring capabilities, though with different scope, granularity, and integration options. AWS provides VPC traffic mirroring as its packet capture solution. Traffic mirroring copies inbound and outbound traffic from elastic network interfaces and sends the copies to a monitoring destination, either a network load balancer or an ENI of a monitoring appliance. Mirror sessions define the source ENI, the target, and optionally filter rules that specify which packets to mirror based on protocol, port, and direction. This enables selective mirroring of only relevant traffic types, such as only HTTP traffic or only traffic to a specific destination, which reduces the bandwidth overhead of mirroring. The mirrored packets are encapsulated in VXLAN headers before delivery to the target. Traffic mirroring is particularly useful for running IDS tools like Suricata or Zeek on mirrored traffic without placing them inline in the traffic path. AWS charges per hour per mirror session and per gigabytes of mirrored traffic. Azure provides packet capture capabilities through Azure Network Watcher. The packet capture feature can be triggered on a specific virtual machine and captures packets to a storage account or to the virtual machine's local disk. Network Watcher packet capture supports filter conditions including local IP, remote IP, local port, remote port, and protocol. The capture runs for a specified duration or until a specified file size is reached. For larger scale or continuous capture scenarios, Azure supports deploying third-party network monitoring appliances through Azure Marketplace. Vendors such as ExtraHop, Gigamon, and Corelight provide virtual taps that integrate with Azure's networking fabric. Azure does not have a native equivalent to AWS traffic mirroring that continuously mirrors all traffic from an interface to a collector. The Network Watcher packet capture is more of an on-demand diagnostic tool than a continuous monitoring solution. Google CP provides packet mirroring as its traffic capture service. Unlike AWS traffic mirroring, which operates at the individual ENI level, Google CP packet mirroring operates at a broader scope. You can mirror traffic from all instances in a subnet, all instances with a specific network tag, or all instances in the VP circuit. The mirrored traffic is sent to an internal load balancer that fronts a fleet of collector instances running IDS or monitoring software. Google CP packet mirroring captures both ingress and egress traffic and includes the full packet payload up to the MTU size. Because the load balancer is used as the collector target, the mirroring solution can scale horizontally by adding more collector instances behind the load balancer. Google CP charges for packet mirroring based on the amount of data mirrored. Google CP also provides the Network Intelligence Center, which includes connectivity tests, firewall insights, network topology visualization, and performance dashboard for ongoing network observability beyond raw packet capture. Private access to cloud storage services. Object storage services Amazon S3, Azure Blob Storage, and Google Cloud Storage are among the most heavily used cloud services. By default, these services are accessed over the public internet using HTTPS. For organizations with strict data security requirements, compliance mandates, or performance needs, accessing storage services entirely within the private network without traversing the public internet is essential. Each cloud provides specific mechanisms for this private storage access. AWS provides two mechanisms for private S3 access from within a VPC. The first is the S3 Gateway Endpoint, which is a free, route table-based mechanism that routes S3-bound traffic through AWS's internal network rather than the Internet Gateway. The Gateway Endpoint creates a route entry in the subnet's route table pointing to the endpoint for S3 prefixes in that region. Traffic never leaves the AWS network and no additional IP addresses are consumed. However, gateway endpoints are limited to the same region as the VPC and cannot be accessed from on-premises over VPN or Direct Connect. The second mechanism is S3 interface endpoints, powered by AWS Private Link, which create ENIs with private IPs in your subnets. These can be accessed from on-premises through Direct Connect or VPN, making them the correct choice for hybrid environments. S3 bucket policies can enforce that all access must come through a specific VPC endpoint, preventing any internet-based access even from users with valid credentials. Azure provides two mechanisms for private blob storage access. The first is service endpoints for Azure Storage, which extend your VNet's identity to the storage account and route traffic through the Azure backbone rather than the Internet. The storage account's firewall can be configured to allow access only from specific VNet subnets that have the storage service endpoint enabled. Like AWS Gateway Endpoints, service endpoints are a VNet internal mechanism and traffic still exits the VNet routing domain to reach the storage service. It does not provide a private IP for the storage endpoint. The second mechanism is private endpoints for Azure Storage, which provide a private IP address within your VNet subnet that maps to your storage account. DNS for the storage account's FQDN is resolved to the private IP using Azure Private DNS Zones with the private link.blob.core.windows.net zone. Private endpoints support access from on-premises over ExpressRoute or VPN, fully satisfying data residency and compliance requirements. Google CP provides private Google Access as its mechanism for accessing Google Cloud Storage and other Google APIs from virtual machines without external IP addresses. When private Google Access is enabled on a subnet, virtual machines in that subnet can reach Google APIs using their internal IP addresses, routing traffic through the Google CP network to the googleoffice.com domain rather than through the Internet. Google CP also provides Private Service Connect for Google APIs, which creates a PSC endpoint of forwarding rule with a private IP in your VPC that resolves to the Google API service. This endpoint can be given a custom DNS name and can be used from on-premises over Cloud Interconnect or HAVPN. Cloud Storage Bucket IAM policies combined with VPC service controls perimeters can enforce that storage access is restricted to authorized VPCs, preventing data exfiltration through compromised credentials from unauthorized network locations. Global network backbone and traffic routing tiers. One of the most significant but least visible differentiators between the three cloud providers is the quality, reach, and utilization of their global private network backbones. When traffic traverses from one region to another, the routing path, whether over the cloud's private global backbone or over the public internet, has a substantial impact on latency, packet loss, and overall reliability. Understanding how each cloud routes inter-region traffic is important for global application architectures. AWS operates a private global backbone network called the AWS Global Network. All inter-region traffic between AWS services, VPCs, and AWS backbone services travels over this private network rather than the public internet. When you transfer data between two S3 buckets in different regions, replicate data across RDS read replicas, or route traffic through a transit gateway inter-region peering connection, that traffic traverses the AWS backbone. AWS makes this backbone available to customers explicitly through AWS Global Accelerator, a service that uses Anycast to route user traffic from the nearest AWS Edge POP into the AWS backbone for the remainder of the journey to the API endpoint, rather than traversing the variable quality public internet from the user's ISP to the application region. This can reduce latency by up to 60% and significantly improve tail latency for applications serving globally distributed users. Azure operates a global WAN backbone called the Microsoft Global Network, one of the largest private networks in the world, with over 200,000 kilometers of fiber and more than 175 network POPs. Azure inter-region traffic between VNets, between Azure services, and through virtual WAN hubs routes over this backbone. Azure Express Route Global Reach leverages this backbone to connect two on-premises sites through Azure's network, using it as a transit WAN. Azure does not offer a customer-facing service equivalent to AWS Global Accelerator for routing user internet traffic over the Microsoft backbone. This function is partially served by Azure Front Door, which accepts traffic at edge POPs and routes it over the Microsoft backbone to Azure regions, combining CDN and acceleration functions. Google Cloud Platform operates what it calls the Jupyter Network Fabric and the Espresso peering infrastructure as the foundation of its global backbone. Google Cloud Platform is unique among the three clouds in offering an explicit network service tier model. Premium tier routes traffic from the user's device over the public internet only to the nearest Google point of presence and then carries it entirely over Google's private backbone to the destination region. Standard tier routes traffic over the public internet from origin to destination, with Google's network involved only within the region. Premium tier is the default and provides the lowest latency and highest reliability for globally distributed workloads, but at a higher per gigabyte cost. Standard tier is appropriate for workloads that are inherently regional and do not require global traffic optimization. This explicit tier choice gives Google Cloud Platform customers the most transparent control over the routing quality and cost trade-off among the three clouds. Network observability, monitoring, alerting, and analytics platforms. Beyond flow logs and packet capture, comprehensive network observability requires integration with monitoring, alerting, and analytics platforms that can correlate network telemetry with application performance data, surface anomalies, and trigger automated responses. Each cloud provides native observability tooling specifically for network resources, integrated with their broader monitoring and operations platforms. AWS provides Amazon CloudWatch as the central observability platform for network resources. CloudWatch collects metrics from VPC components including NAT gateway throughput and connection counts, load balancer request rates and error rates, VPN tunnel state and throughput, direct connect connection state and bandwidth utilization, and transit gateway packets processed. CloudWatch Logs receives VPC flow logs, network firewall alarm logs, and Route 53 query logs. CloudWatch alarms can trigger SNS notifications, auto-scaling actions, or Lambda functions based on network metric thresholds. For example, alerting when NAT gateway packet drop counts exceed a threshold indicating SNAT exhaustion. AWS Network Manager provides a centralized dashboard for monitoring transit gateway network topologies, including route analysis, event history, and network performance metrics across a global network spanning multiple regions and on-premises locations. AWS also integrates with third-party observability tools through CloudWatch metric streams and Kinesis Firehose for high-throughput telemetry export. Azure provides Azure Monitor as its unified observability platform for network resources. Azure Monitor Network Insights provides a dedicated dashboard view for network health, showing topology maps, connection monitors, traffic flow summaries, and diagnostic recommendations across all network resources in a subscription. Azure Network Watcher provides connection monitoring between endpoint pairs with continuous latency and reachability tracking. Azure Monitor Metrics collects performance data from ExpressRoute circuits, VPN gateways, application gateways, load balancers, Azure Firewall, and other network resources, with configurable alarm rules and action groups. Azure Monitor workbooks allow operators to build custom network observability dashboards combining metrics, logs, and topology data. Traffic Analytics, built on top of NSG flow logs and log analytics, provides a geographic visualization of traffic origins, top talkers, and anomalous patterns, including traffic to known malicious IPs from the Microsoft Threat Intelligence feed. Google CP provides the Network Intelligence Center as its dedicated network observability and analytics platform. The Network Intelligence Center includes 5 modules. Topology shows a real-time graph of your VPC networks and their interconnections. Connectivity Tests analyzes paths between endpoints as described earlier. Performance Dashboard provides aggregated latency and packet loss metrics between Google CP regions, measured continuously using probing infrastructure, giving operators baseline performance data for their network paths. Firewall Insights analyzes firewall rule usage, identifies shadow rules that are never hit because another rule takes precedence, and recommends rule removals or simplifications. Network Analyzer is the newest module, which continuously analyzes VPC configurations and surfaces potential issues such as misconfigured routes, overlapping firewall rules, subnet exhaustion warnings, and suboptimal BGP configurations, providing proactive recommendations before issues impact workloads. Google CP also integrates with cloud monitoring for metric-based alerting on network resources, including cloud NAT allocation failures, VPN tunnel states, and load balancer backend health.